Okay, so today our topic is motion planning, and also sometime we call it as a trajectory planning. And today it will be new experience from me because I am not able to see you, but you are able to see me, and I am continue teaching, hoping that within few minutes your control room will take care of this. So, the announcements for today is that outlines of lecture 25 are available at the following website, and also the figures of chapter 11 are also there in this website. It will be ch11fig.pdf, ch11fig.pdf, just like other chapter figures. And at the end of the class, I will request the following students to come in front of the camera, hoping that I will be able to see by that time, and then we will have discussion. So, the review of our last lecture, there was a DC motor model was developed, a link model with gearbox was also modeled, and then transfer function of a robot joint, that means DC motor plus the link, was derived, and then the different control schemes were shown, which were proportional plus derivative, we call it PD control, and proportional integral plus derivative, which is called PID control. So, today we will be starting with a new topic. This is chapter 11 of my book. First, we will talk about introduction, where we will see why trajectory planning is important. Then we will see planning in joint space, that means you define the joint motions, not the end effector motion. So, there you will see how yes, now I can see you that fifth order polynomial is one of the useful functions to define the joints angles. Then we will see with certain conditions we can simplify fifth order polynomial to fourth order polynomial also. Then some combination of fourth order polynomial with straight lines can be obtained when the initial and final points are given. We will see through an example, and then we will talk about Cartesian space planning. That means, instead of defining the joint angles, I can define directly the end effector positions. So, we will see the position trajectory. There is also requirement of rotation trajectory, which we will take up in the next class, and finally, the summary. So, the first question is why motion planning, right? Like if you are walking, if you are asked to go from your university to home, now how you go? You plan, right? You plan that you take which door to exit, and then which stairs to follow, and then once you are coming out of your university, which road to follow, right? So, just like a person to decide a route from one place to another, a robot's path needs to be decided through motion planning, right. So, for you, your brain as a computer does all the planning almost instantly based on your earlier experiences. Here those experiences have to be put by the programmer into the controller of the robot. So, goal of the motion planning is to generate a function according to which a robot will move. For example, if it has to move from point A to point B, whether it should go in a straight line fashion, whether it will go in a circular fashion, whether it will go in a sinusoidal fashion, no. So, motion planning will decide that path. So, but this function generations now will depend on your task, right. The task could be, say, pick up an object from one point to a place it in another point. So, you pick up from one point, look at my hand. So, suppose my hand is a robot. If my task is to pick up one object from here and place it here. So, this is one task, I pick it from here and place it here. Now, whether I go pick it, I go like this, place it here, or I pick it from here, go like this, place it here. So, that is the task of motion generation, or I can pick it from here and go place it here. So, how we go, that is the task of a motion planning. So, this is called pick and place operation, pick and place operation, right. But if I have to do the welding, right, so I have to do some welding on some surfaces, right. So, I have to join two cylindrical pipes. So, I have to do the welding like that way, right. So, here I cannot go to my desired choice that okay, I start from here and go there. No, that is not possible. I have to go along this circular path, go slowly and do this job, right. So, here at very finite interval, very small interval, the points will be provided. So, between very small distance, you may imagine it is a pick and place operation from here to here, right. But actually it's a continuous path. So, we call it a continuous path, and this we call it a pick and place operations. Okay. So, these are the two major tasks robots perform in an industrial setup: pick up an object from one point to place it in another point, or to weld two metal pieces along a curve. So, for your information, motion planning is also called trajectory planning, right. So, motion or trajectory planning, because ultimately we are talking about a trajectory along which the robot moves, be it a pick and place, be it a continuous, ultimately it follows a certain trajectory. Now, in joint space, look at my hand now. Suppose if I move from this point to this point, I can imagine that this is a movement of this end effector along x directions by certain amount. I can also imagine this is a motion provided by this joint. Okay. So, I can think it is a motion in the end effector, we call it end effector space. That means, I say x is equal to constant. Suppose if your coordinate frame is somewhere else on this room. So, I can say that along x direction it is having some variable quantity, but all other direction it is constant. Or to achieve these motions, what I am doing is I am basically rotating this, okay. But while I rotate it, it will do a circular arc. So, just this rotation is not sufficient, I have to rotate this side also to maintain the straight lines, right. So, I can imagine that when I am moving this way, I can imagine it is a rotation of my this joint here plus this joint. Okay. So, rotation, the translation of the end effector along certain path is equivalent to certain rotations of my these joints. Okay. So, I can think of providing a motion in terms of joints. So, we call it a joint space motion, or we can think of end effector motion, we call it a Cartesian space motion, because we are defining in terms of x, y, z. And during our inverse kinematics, we have seen that how this position can be related with this joint. Okay. Go back to the slide now. So, when we say trajectory planning, it could be in joint space. That means, you tell me at the first position what was the joint, and in the second position or the last positions what was the joint. Okay. So, knowing these two joint angles, I can decide what trajectory I want to follow, and then correspondingly I can find out the velocities and accelerations. We call it a joint space trajectory planning. Suppose if you have provided the motion in end effector motion x, y, z, then we call it a Cartesian space or operational space, because after all the robot is working in this Cartesian space by moving an object from an xyz location to another xyz location. So, in these variables we call it a operational space, and there we define end effector positions, we define end effector orientations and their time derivatives, because they are required for my dynamic calculation. Now, for a human being we can understand much better if you tell me, sir, I have moved from 1, 2, 3 location to 4, 5, 6 location, which I can quickly understand. But if you tell me, sir, I have moved from theta 1 from 10 degree to 30 degrees, theta 2 30 degree to 50 degrees, theta 3 from 60 degree to 90 degrees, unless I have a robot in front of me, I do not understand anything. Okay. So, the Cartesian space is preferred as it allows a natural description. It says it allows a natural description of the task that robot has to perform. But the controlling action comes from the joint space, because I have showed you in my hand, please see it again. I have a motor here which can rotate, I have a motor here which can rotate. So, motor does not know what is happening there x, y, z. Rotor knows how much rotation has to happen, which is controlled by a computer. So, since the control of a robot is done by the joint motions, so at the end we need a joint informations. Okay. So, control action has to come from the joint space. So, that is the last line here. The control action on the robot is carried in the joint space. So, we need information in terms of joint space. So, here inverse kinematics plays a very important role, because we human being understand better in Cartesian space, but robot understands better in joint space. So, a suitable inverse kinematic algorithm is to be used to reconstruct the time sequence of the joint variables corresponding to the sequence of the Cartesian space. So, in other words, whatever x, y, z of the end effector is given by an user, we have to convert into a corresponding joint angles, as we have done in our inverse kinematics exercises. Okay. Once we have done that exercise, then we can do the path planning or motion planning, or what we call also as a trajectory planning. So, now I use the slides to demonstrate this concept little better. Again, I take the example of a simple two link case. Okay. Now, this is my end effector. I want to move from point A to point B. So, this is A, this is B, and this is how I want to go. Here I am not specifying. I said this has a coordinate x1, y1, and this has a coordinate x2, y2. I want to go from here to here. How I want to go, I am not specifying. So, what I am doing here is corresponding to x1, y1, this is my theta 1, 1, and this is my theta 2, 1. That means theta 1 corresponding to first position, or let us put it A, and this is theta 2 A. Okay. So, from here now it goes to the other positions. So, maybe it will go here and then there. Okay. So, the red position here for me theta 1 B, and then corresponding to the second positions it will be 0, it appears like a 0 here. So, you can imagine theta 2 B. let me draw a clearer picture. Let us say this is one position. So, theta 1 A, theta 2 A, from there it goes to a new positions. So, this will be rotating in a circle. So, it comes here and then it will be also rotating in a circle like this. So, this is your theta 1 B and then this will be your theta 2 B. Okay. So, this is your position A and this is your position B. Okay. So, I calculate what is my theta 1 A, theta 2 A, I calculate theta 1 B and theta 2 B using, so find theta 1 A, theta 2 A and theta 1 B, theta 2 B using inverse kinematic. Okay. So, once I have found out this, now I can think, now I can plot, now I am plotting say theta 1 versus time t. Okay. So, this is my theta 1 A, okay, and this is my at time equal to 0, and here say I have theta 1 B. So, now I am talking about this angle to that angle, how one should move. Okay. So, we theta 1 A to theta 2 B. Now, how to go from this point to this point, that is the planning I will do now. Whether I want to go straight line or I want to go in a circular path like this, or I want to go a circular path like that, or I want to go in a sinusoidal path like this will be my choice. Okay. So, similarly for theta 2, I may have theta 2A, theta 2A and theta 2B. Again for time I have it here. So, now let us talk about a general theta, be theta 1 or theta 2. Let us talk about just theta. Okay. When I will be talking about first joint, I will do the trajectory planning for the first one. When I will be doing for the second one, we will do for the second one. Okay. Let us say general theta may be the first one. Okay. Say theta 1 is equal to theta, and theta 1 A I call it as a theta 0 and theta 1 B is theta f. Okay, which means, so initially at t equal to 0 and t equal to Tf, so I have theta 0 and theta f, and I am thinking how to join these 2 points. Okay. Now, for that I can do any curve I like, but sometimes there are conditions you may put. Suppose you are telling at t equal to 0, theta dot means the velocity should be some value you specify. You also say that acceleration should be also some value, and then you also specify when it stops, theta double dot should be some value, theta dot should be some value, and you also say the acceleration should be some value which is like this. No? So, how many conditions I have? I have here that at t equal to 0, theta is theta 0 and I have theta at at t equal to 0, at t equal to Tf I have theta is equal to theta f. So, if you look at it, I have now so many conditions to be satisfied. I have one condition here, I have another 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 condition here, and I have another condition here. So, 1, 2, 3, 4, 5, 6. So, you are putting 6 conditions that my initial time at t equal to 0. So, this is your t equal to 0 and this is t equal to Tf. I want my positions, velocities, acceleration as per my wish. Here position, velocity, acceleration as per my wish. Now, such conditions can be satisfied using many different functions. But one of the easy function would be a polynomial. So, a simple function that will satisfy all 6 condition is theta is a0 plus a1t plus a2t square plus a3t cube plus a4 t4 plus a5 t5. So, this is one very popular function which can satisfy all 6 conditions, but the question is, for these conditions I need to find out what is this, 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 what is this. So, 1, 2, 3, 4, 5, 6. So, I should be able to find all these 6 coefficients which should be possible to satisfy all these conditions. Let us see how that is done. So, what did I say? At t equal to 0 here, theta is equal to theta 0. So, let me put this condition in this general function. So, at t equal to 0 means this is 0. So, theta 0 is a 0 plus at t equal to 0 means this I should be putting 0. So, this term will be 0. I should be putting t equal to 0, this will be 0. So, all these things will be 0. So, from these conditions I find a 0 is nothing but theta 0. Then the second condition is at t equal to Tf, theta is equal to theta f. So, let me put that condition, theta f is equal to a 0 plus a 1 Tf. So, this should be user specified. You should tell that after 3 seconds this should be the value. So, this is known. When I put f, that means this is known, a2 Tf square plus a3 Tf cube plus a4 Tf4 plus a5 Tf5. This value I have calculated from above. So, I put this value, this will be theta 0 plus a1 Tf whatever I have written here. So, I have in these equations I have now still how many 1 to 5 coefficients have to find. So, I have to use now other conditions. So, other condition is at t equal to 0 theta dot equal to theta 0 dot. So, let us use that thing, for which I need theta dot expressions. So, theta dot is equal to A1 plus 2A2 t plus 3A3 t square plus 4A4 t cube plus 5A5 t4. So, now I put this condition that at t equal to 0, theta dot equal to theta 0 dot. So, I put this. So, this will be my theta O 0 dot is equal to A1 plus, so at t equal to 0, so all 0. So, this is all 0. So, this gives me A1 equal to theta 0 dot. Then the condition theta f dot should be equal to A1 I have calculated theta 0 dot plus 2A2 Tf plus 3A3 Tf square plus 4A4 Tf cube plus 5A5 Tf 4. Okay. So, I have used two conditions for positions, I have used two positions for velocities. So, I could calculate two coefficients, one coefficient here, another coefficient here. Okay. Now, proceed to put the condition for the third, that means the accelerations. So, for the accelerations now I need a theta double dot. So, I got theta dot here. Okay. So, from here I can get, it will be 2A2. So, I am writing 2A2 plus 2A2 plus 6A3t. So, I am putting 6A3t, okay. Then plus here 4A4t cube, 4A4t cube, that means 12A4t square. So, 12A4t square plus 5 into 4, 20A4t cube. So, 20A5t cube. Okay. So, now again I put those conditions that at t equal to 0, theta double dot equal to theta 0 double dot. So, I put that value. So, theta 0 double dot is equal to 2A2 plus, these are all at zeros. So, these are zeros. So, from there I can get A2 is equal to theta 0 double dot by 2. So, another coefficients are obtained. So, I could get, now I have another condition, theta f double dot is equal to 2A2 is theta 0 double dot plus 6A3 Tf plus 12A4 Tf square plus 20A5 Tf cube. So, I could calculate three coefficients A0, A1, A2, and I have three equations. This I have calculated, this I have calculated A0, A1 and A2, but I have other equations. One is these equations, one will be these equations, and then the third one will be these equations. So, in these equations, how many unknowns I have? In this equation I have A1 already calculated. Now, I will put those values now. So, theta f is equal to theta 0 plus theta f is equal to theta 0 plus A1 is calculated as theta 0 dot into Tf, and A2 is calculated as theta 0 double dot by 2 Tf square plus A3 Tf cube plus A4 Tf4 plus A5 Tf5 and then you have theta f dot is equal to theta 0 dot plus 2a2 will be theta 0 double dot Tf plus 3a3 Tf cube of 3 square plus 4a4 Tf cube plus 5a5 Tf4. So, now if you notice, this is known to me, 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 this is known to me. What is also known to me is this, because Tf I am providing, this is known, this is known, this is known, this is known. So, ultimately I have 3 equations in 3 unknowns, and which are the unknowns? Unknowns are A3, A4, A5. So, if you put little effort, you can use these 3 equations 1, 2 and 3, and then you should be able to calculate what is A3, A4, A5. So, 3 equations, 3 unknowns can provide solutions for A3, A4, A5. Okay. So, now I will show you these 3 solutions along with the other solutions A0, A1, A2, so that our polynomials of what we call 5th order. The polynomial, a simple function that will satisfy all 6 conditions, is this one. This is 5th order polynomial, okay, function in t, t means time. So, this is called 5th order polynomial function in t. So, I repeat, I have solved this from the conditions, I have solved this from the conditions, I have solved this from the conditions, and I have these 3 equations from the conditions, which I should be able to solve to calculate A3, A4, A5, which I will show you on the screen. So, in these lines I am just stating what I have done, just for your understanding. Let me repeat quickly. So, this is theta at time equal to 0, theta 0, theta equal to time equal to f is theta f, theta, this is, we call it a velocity at 0, velocity at time f, acceleration at 0, acceleration at time f, and these are those equations which I have written. So, polynomials of time t are chosen due to their ease of computation and simplicity of expressions. Lowest order that can satisfy all the above 6 conditions is 5, which I have also done on my script and handwritten page, and here are the solutions. A0 equal to theta 0, I have shown you how to calculate. A1 is theta 0 dot, I have shown you how to calculate. A2 is equal to half theta 0 double dot, I have shown you how to calculate. Then using those 3 equations, now I have solved for other coefficients, which are A3, which is given by long expressions, then A4. So, this is A4. They are not very difficult. If you try to check if the results are correct or not, you can do it very easily. And then the last one is A5 is this much. So, now you have a 5th order polynomial which will satisfy all 6 conditions which we call as a position conditions, velocity condition and acceleration condition. You might be asking these questions, why we are putting velocity and acceleration conditions. Okay. Now, sometime if you want a smooth motion, you want the velocity at the starting at the end should be 0. Assume that you are running and somebody just wanted to stop you. What will happen? There will be big kind of an impact. So, if the robot is moving at certain speed and suddenly you want to stop, there will be big impact on the robot. We do not want a impact on the robot. Okay. So, we want a smooth motion. So, sometimes we want to stop the robot with a 0 velocity and 0 acceleration, and same thing we do not want to start suddenly. Assume somebody is pushing you from the back, want you to start running suddenly. So, there will be again jerk, we do not want. So, for those purposes we want to control the velocity and acceleration both at the beginning and at the end. Okay, now there is an interesting thing here. Suppose if the endpoint accelerations are vanishing, means if you are putting theta 0 double dot and theta f double dot equal to 0, okay, which means you are starting with 0 acceleration and ending with 0 accelerations, then at these expressions they will simplify. You see theta 0 double dot, if I put a 0 and also I put theta f double dot is equal to 0. So, this term is completely vanishing. Okay. Similarly, this term will completely vanish and this term will simply vanish. So, if my end accelerations are 0, so my coefficient equations are simple. So, only I have to do this much. Now, imagine theta f minus theta 0 is equal to T f by 2 into theta 0 dot plus theta f dot. If I imagine my initial position and my final position difference is equal to the average velocity at the beginning at the end and multiplied by T f, what will happen? So, what I do is I substitute this expression. So, what did I do? Theta f minus theta 0 is considered as theta f dot, I am just trying to write from the next page, then this is theta 0 dot, okay, then into T f by 2. So, 2 into 12 will become 66. Okay. So, this cancels out. So, then it becomes 6 theta f dot plus theta 0 dot into T f, which is exactly same as this one. So, then this term and this term will cancel out, giving a result of 8.5 is 0. So, what did I get? If my end accelerations are 0 here and if I choose my theta f minus theta 0 in this fashion, I get a5 equal to 0. So, if a5 equal to 0, so then look at this page here. So, if a5 equal to 0, a5 0 means this is 0. So, effectively then I am talking about a polynomial of 4th order. So, this is a 4th order polynomial. So, in other words, if theta, if at time equal to 0, theta is equal to theta 0, then at t equal to Tf, theta is theta f, then you have theta dot is equal to theta 0 dot. At t equal to Tf, this will be theta dot is equal to theta f dot, theta double dot is equal to theta 0. At t equal to Tf, theta double dot is equal to 0 plus theta f minus theta 0 is equal to Tf by 2 theta f dot plus theta 0 dot. So, then theta is equal to a 0 plus a 1 t plus a 2 t square plus a 3 t cube plus a 4 t 4 is good trajectory. In which case a 0 is again the same as what we have calculated, a 1 is theta 0 dot, a 2 is 0, then a 3 can be calculated accordingly, 1 over 2 t f cube 20 theta f minus theta 0 minus 8 f plus theta 0 dot into T f. And similarly, a 4 can be calculated as 1 over 2 T f to the power 4. Let me write in a different page. A 3 you have seen it. So, a 4 I can calculate as 1 over 2 T f to the power 4, then it will be 30 theta 0 minus theta f plus 14 theta f dot plus 16 theta 0 dot into T f. So, then a fourth order polynomial would be good to estimate this trajectory. Now, I wanted to show you the meaning of this condition in graphical manner. What does it mean? So, I mean that this is my 0 theta 0 and at here I have theta f, but the velocity means I have a tangent in this direction, suppose. So, this is a tangent theta 0 dot, theta f dot. So, this is a tangent in this direction. So, this value, let me show you, if this theta f minus theta 0 is this much. So, which means if the difference between the velocities, difference between the position is equal to this one, then we can have fourth order polynomial. So, in addition to those 6 conditions, if we add this following condition, we can have fourth order polynomial to this decide a trajectory. So, here I am writing f(i) equal to 0, which implies that only fourth order polynomial is required for theta t. So, using combinations of fourth order polynomials and straight lines, trajectories of various cases can be determined fairly easily. So, our objective is to connect theta f and theta 0. So, if we make these conditions, then we can use a fourth order polynomial. So, here I wanted to show an exercise. I want to go from this point here, theta O. So, I want to go from this point theta 0 to theta f. There is a mistake here, this is not theta f 3, please correct it. So, this 3 will not be there. So, this will be theta f. So, I want to move from theta 0 to theta f using a trajectory. What is the trajectory? So, one suggestion I give in this exercise, that one trajectory could be that I go from here to here along a fourth order polynomial, from here to there I go along a straight line, and from there to there I do a fourth order polynomial. Why this is so? The reason is I want to start with a 0 acceleration here and I want to finish with a 0 acceleration here. For some reason I do not care what should be my f, there could be some velocities. Okay. So, how to do this kind of trajectory? This is one of the standard trajectory used in industries. Okay. I repeat, I want to go theta 0 to theta f, I will go along a certain fourth order polynomial, straight line, and then the fourth order polynomial. Now, what are the coefficients of these fourth order polynomials? What is the equation of this line, and what is the coefficient of this fourth order polynomial? I am going to derive now. Okay, please listen carefully here. I want to now get the coefficient. So, first thing what I do is, so trajectory is developed that starts from the rest theta 0. Okay. When I say rest, I mean velocity is also 0, passes through phases of acceleration, constant velocity and deceleration, and finally completely stop at theta f. So, value of parameter delta that denotes the 1/2 of the acceleration and deceleration period is chosen. Okay. And auxiliary points theta 02 and theta f1 are determined. Okay. Here is the method. Okay. I think I will show you on the paper as I do for you. So, this is my theta 0 and here this is my Tf and this is my theta f. Okay. So, it says first you choose two, okay, this first you choose certain delta. So, I choose certain delta and the same the other two sides. This is my choice. Okay. I choose some delta and then 2 points theta 01 and theta f1 at time equal to t delta. So, I choose a value here which is theta 01. I choose a value here which is theta f2. This is theta f here. Okay. Then and I take these values in such a way that theta 01 is equal to theta 0 and theta f2 is equal to theta f. Then what I do is, next I connect by a straight line. So, I connect theta 0 1 and theta f 2 are connected by a straight line. So, I connect by a straight line. So, I connect these 2 points by a straight line, okay, and determine as the points on the straight line at time t equal to 2 delta. So, now this point I find out from the straight line. So, 2 delta here. So, this point I calculate, okay. This I give a name between theta 0, this I give a name theta 0 2 and theta I give a name theta f 1, means this value is theta f 1, this value is theta 0 2, okay. Now, I have between these 2 points, between this and between this and that, I plot a fourth order polynomial. So, between these two I have a fourth order polynomial here and there I have a fourth order polynomial. So, this fourth order polynomial between theta f 1 and theta f, okay. So, here fourth order polynomial between theta 0 and theta 0 2, and this is a straight line between theta 0 2 and theta f 1, okay. So, that will complete my trajectory. We will see this with respect to one example which is shown here. So, I take a 2 degree of freedom example. I have a robot which is in this configuration where my link 1 is making an angle 90 degree and link 2 making an angle minus 60 degree, and now this is my first position and I want the robot to move to these positions where this angle is 60 and this angle is 120. Now, I want to have a trajectory of this movement. I do not care how it moves from this point to this point, okay. Only I care is point A here and point B, that is it. So, now, but to move the robot I need certain trajectory because controller has to provide certain trajectory. So, that is a trajectory I will generate using the method I have just explained. So, for that I will show you in detail how to do it for theta 1, that means it is going from 90 to 60. So, let us look at that exercise which I will do it in front of you. Let us move to the paper. So, I will use the same trajectory. So, for me this is 90, this is 60, of course, this cannot be 60. So, I have to redraw the figure. So, I show you so theta 1 goes from 90 to 60, okay, and time I am providing the time, it should be moving in 2 seconds time, okay. Let me just check it. It should be moving in 2 seconds. So, time is 2, this is 0. Okay, this is time, second, and this is degree. Okay, so let's go here. So first I choose delta. Choose delta is equal to 0.25 second. Okay, so delta here, delta here, delta here, delta here. Okay, so now the next thing is I choose theta 0 1. So here theta 0 1 should be equal to 90, and then here, so this will be my theta f2, theta f2. So this is equal to theta 0, this is theta f2 equal to theta f, this will be 60. I am following the method which I have just explained to you. So at t equal to 0.25, theta 0 1 is 90, and at so this means at t equal to 0.25, and here at t equal to 1.75, tf2 is 60, right. So this is 1 point. Now what I do is I join using a straight line, so as per the method. So I join, okay, so I join with a straight line. Now how to find out the equation of the straight line? I assume the equation of the straight line is y equal to mx plus c, okay, or in other words, this is theta 1 is equal to m t plus c, and I know at t equal to 0 theta is 90, so this is equal to 0, so c value is 90, and also I know that theta is equal to 90 at m equal to 0.25. Okay, so from there you can calculate m, because I know this value, right. This I'm sorry, this is plus c, and I also know at 1.75 this is 60, so 60 is equal to m into 1.75 plus c, and from the correlation between these two I can calculate m will be calculated as m will be calculated as minus 20. Okay, so using these two expressions you can calculate m will be minus 20. So your equation will be 1 minute, theta 1 at t equal to 0, sorry, we are talking about this straight line, right. So theta equal to 0 I do not know, this is wrong. So at t equal to 0.25 here, this is 90, this is 90 plus c, at 1.75 this is 60, this is 60, so this is c. So if you now solve these two equations, you will get c is equal to 95 and m equal to minus 20. Okay, so your theta 1 line equation will be minus 20t plus 95. So this will be minus 20t plus 95. Okay, it can be checked from here. If you subtract this thing, so you will get the m value, and then if you substitute the m value here, you will get the c value. So this equation is obtained. So but now from there I need to calculate this value, and from here I need to calculate this value. So, now substituting t equal to 0.5, theta 1 will be minus 20 into 0.5 plus 95. So, this will become 85. Okay. So, this value will be 85. Okay. And similarly, you can calculate t equal to 1.5 because this value is 1.5. So, theta 1 is minus 20 into 1.5 plus 95. So, this will be 65. So, this will be 30 as 65. So, this value is 65. Okay. So, now we want to draw a polynomial between, so fourth order polynomials between 90 degree and 85 degree and 65 degree and 60 degree. Okay. So, now we use the same methods as I have explained, and it will give, we will be able to calculate A0, A1, A2, A3 and A4. So, A0 we know this is equal to theta 0, which is 90. Okay. A1 theta 0 dot 0, that means started at rest. If it rest means velocity was 0. A2 was equal to 0, condition for fourth order polynomial. Okay. So, A3 and A4 I have calculated as minus 80 and A4 I have calculated as plus 80. So, calculated using formulas. Okay. So, that way now so this is between time period of between t is equal to 0.5 and 0. So, this is between t 0 and 0.5 means between this period, because this I have joined as a polynomial. So, between 0 to 0.5. So, between 0 to 0.5 I have got this polynomial. So, between 0 and 0.5 I have the values for this polynomial. In other words, if I write the polynomials, theta 1 is 90 minus 80 t cube plus 80 t4, this is 0 t is 0.5. Okay. So, between this and this it is polynomial, between this and this it is a straight line. So, I write theta 1 is 85 minus 20 t minus 0.5, this will be 0.5 t less than 1.5, because this is the straight line, and the finally this portion is again a polynomial here. So, I draw another polynomial theta 1 is equal to 65 minus 20 t minus 1.5 plus 80 t minus 1.5 cube minus 80 t minus 1.5 to the power 4, and this will be between 1.5 t and 2. So, these are actually the knowledge from geometry. Okay. So, I am not doing anything else, I am just writing a coordinate geometry, I am just writing equation of curves. So, in this case it is a, for the first zone this is the one, for the second zone this is the one, and for the last zone this is the one. So, when a control signal has to go to the computer, so depending on at what time, so depending on the values of t, it will first check that at what period I want to calculate. So, it will calculate theta 1 if it is in this, if it is in this zone it will calculate using the second function, if it is in this zone it will use the third function, and that is the way it will calculate the joint trajectory for the first one. So, if you want to know what happens to the second one, that I have on my slide. So, if you can come to my slide. So, this is for the first one. So, this is for the first one. I have shown you how to derive for the straight line and the first polynomial, rest I leave it for your practice. Okay. If you have difficulties later you will ask me. For the joint 2, I can similarly find out the motion which is from 60 degree to 120 degree, right. So, for the second motion, for the motion this is 60 to 120. So, this is, and you can calculate as a homework that these are the equations you are getting. Now, you must be now interested to know how the motion happens. Okay. So, this is the way motion happens actually, right. It started at t equal to 0, okay, and then at t equal to 5, at t equal to 5.5 this is the 1, t equal to 1 this is the 1, 1.5 here and 0.0 here. It started with, this angle was 90 degree. So, this angle was 90 degree at the beginning, and at the end this was 60 degree. So, it has traversed 30 degrees. So, you can see 5, 10, 10, 5 it has traversed, and the second motion was, second joint, it was here you had 60 degrees, and then here you had 120 degrees. Okay. So, this is your 60 here, and this is your 120, and I have now used a forward kinematics to calculate where is this position is, and I have plotted in this diagram. Okay. So, in end effector domain or end effector space, actually it has moved like this thing, even though your theta 1 movement, if I plot your theta 1 movement, it was something like curvy nature, then straight line, and then again some curvy nature. Theta 2 exactly the same curve, but with the different values, but in xy motion what is shown is the final motion. Okay. So, if you want to do in a Cartesian space, that means I say no, I do not want to give you the path in joint, no, you do not give the path in joint motion, you tell me in these motions only. Okay. Then how it will happen, that is the next step. In Cartesian space, like in the previous case, You see the range between 0 to 0.5, the distance it has traversed is different than 0.5 to 1. Okay. So, this distance is more than that. We are not able to control this distance. Okay. And even though it is a 5 degree here, it is 10 degree here, that means twice it has moved, but this you cannot correlate that whether this distance is half of that. So, in welding I want to control at t equal to 0 it is here, maybe 0.5 it is here, 1 it is here at equal distance. So, if you want to do in equal distance, you better do the trajectory planning in Cartesian space, which is my next slide. So, in arc welding the electrode should follow a seam precisely. In such cases we wish to generate a trajectory in terms of the position and orientation variables of the end effector. There are several ways to describe the position and orientation, that is configuration of the end effector, and we need 6 variables, 3 for positions and 3 for orientations. Here I am showing an example of the same robot, but drawn in a Cartesian trajectory plan in a position. Suppose if I want to move R0 is the position of the end effector from this position to this position, then I can calculate my trajectory in exactly the same manner, that x function of time will be this, and first is the 4th order polynomial, then the straight line, and then the 4th order polynomial, and y 4th order polynomial, then the straight line and the 4th order polynomial. If you want to see the plot, so now you see this is my plot. So, t equal to 0, t equal to 0.5, t equal to 1, t equal to 1.5, t equal to 0. Note the difference, I wanted to move in a straight line fashion. Okay. So, if I do it in a Cartesian trajectory, so this is the trajectory I have generated, whereas corresponding theta 1s are shown here. Okay. So, if you have done the trajectory planning in the Cartesian space like shown here, and if you want to control the robot, obviously you have to do the inverse kinematics for these positions. So, of course, this will be one of the difficulties. So, inverse kinematic here I write it as I, corresponding to this another inverse kinematics here, for here another inverse kinematics here, for here another inverse kinematics here, and they are also inverse kinematics. So, if you do a trajectory planning like this, to control this robot you have to do 1, 2, 3, 4, 5 times inverse kinematics, and this is the complications for continuous or end effector trajectory planning. But in the previous case, you have done only one inverse kinematics here, and you have done another inverse kinematics here. So, another inverse kinematics here, and rest of the motions you have done it in the joint space. So, only 2 inverse kinematics, joint trajectory planning, and here if you do the Cartesian trajectory planning you have to do 5 times, but sometime application demands this kind of trajectory planning. So, we have to perform inverse kinematics 5 times. So, with this I will stop today's presentation. Need for motion planning is explained, joint space planning is introduced, 5th and 4th order polynomials were also obtained, and Cartesian space planning was given and examples were shown. Okay. So, now very quickly I want these following 6 students come into the front bench and ask me quick questions. We have about 6 minutes. Abraham Bekele, please raise your hand also. Abraham Bekele, raise your hand. Absent? Okay. Come front. Alemake Failu? Okay, fine. Baleigze Negus, raise your hand. Absent? Okay. Bereket Kebede, raise your hand. Okay, fine. Biruk Jenberu? Okay, fine. Demeke Abu Said? Demeke is absent. Demeke is red. Gebru Amare, come in the front, come in the front bench. And Goitam Tesfaye, raise your hand. Okay, please come in the front. Any questions? Who has the question? Abraham, you have question?
Can you hear me?
Yes, now I can hear you.
Okay. I just need some clarification on the concepts of multi-input, multi-output robot control system and
Right.
single input, single output
Okay.
robot control system.
Okay.
Clarification on this concept.
Okay. Multi-input, multi-output. A robot has many motors. Say one motor here, another motor here, and say another motor here. Let's say 3 motors, right? Now 3 motors require 3 different control, because if I control this thing, okay, so then when I move this thing, my motion gets affected here. So I can when I move this thing, since this motion is, when I am moving it, it has a effect on the whole arm. So when this arm has to move a different motion, so motion of this thing has to be taken into account by this motor also. So when this motor is working, this motor cannot work independently, because the motion of this motor has the effect on the performance of this motor, because the whole arm is moving. So this is called multiple input, multiple output, because the 3 motor input and output cannot be thought independently, right? Motion of this thing has the effect on this, effect on this motor has the effect on that. So 3 parallel motions have to and control action has to come 3 simultaneously. But if you have this motor with a very high reduction gear, then this motion here has negligible effect on this. So it has only, this motion is only important, this motion has no effect on this one. Okay. So then I can think that the rotation of this and whatever the fixed weight it has, I can treat it as an independent of this motion. So I do not look at this motor's performance, only this motor can work independently. So that is called single input, single. So 3 motors can be thought of as a 3 independent motors without knowing what is happening to the other motors. Okay. Is that clear? Basic thing is, when this motor is moving, its inertia changes from this position to this position. So this motor, when it has to rotate, it has to understand what is happening here. But if the gear ratio is very high, we have seen that this effect has no meaning to this motor. It does not understand, because it has a very high gear ratio. So it does not understand whether it is here and here, and so it can be thought of as a separate motor without knowing what is happening. So it is called independent control or single control. Any other question? Gautam, what is your question, Gautam? Gautam.
Okay. What do you mean effective inertia? Would you explain effective inertia?
Please speak slowly.
Effective inertia.
Effective inertia.
Yeah.
Okay. Effective inertia is suppose let's make a drawing for you. Now, in this system, suppose if I substitute this gear reduction and the link by a system, suppose you do not know what is inside. Okay, what is the inertia? What is inertia of this system? Okay, this system means it is an equivalent to gear reduction plus link, right? So, then we say that this is I of m plus it is I of L by eta square. So, I m is this m which is here. So, let us take it the link here. Okay, this is. So, I m is this portion and I L is this portion and this is eta square. So, if you want to think this whole arrangement as one link, then this link inertia is this one. It is an effective inertia, means if this gearbox has an effect on the dynamic motion. Okay. So, this is called effective inertia. Suppose if I give you what is the, you have a mass here m1 and I put a mass on the top of it m2. So, what is the effective mass? What is your answer?
I think the sum of the two mass.
Yes. So, in this case m effective is m1 plus m2. So, similarly for rotational case with a gearbox, so this is the effect. So, if you think of it as a total mass, this is m1 plus m2, this is, so this in case of rotation we derive from the equations of motion as we have done in our lectures. Okay.
Okay, thank you.
Okay, since time is up, if there is a quick questions I can take it, otherwise we will stop. Okay, thank you.